Um, Hi, everyone. Today, I would like to talk about my work on characterizing derandomization through hardness of Levin-Kolmogorov complexity. And this is joint work with Professor Rafael at Cornell Tech. Today, we're going to focus on randomness in computation. And in the very early days, people have discovered that randomness might be useful in computation. And we can probably come up with better algorithms if we can get access to randomness. And now we have randomized algorithms for various of decisional and search problems. So the question is randomness inherent to solve these problems? And for some of them, we know the answer, such as primality testing. And for some of them, we don't know the answer. For example, circuit acceptance probability problem. And in fact, this problem is actually BPP complete. So this question becomes whether BPP equals P. And in this talk, we will refer to promise BPP as just BPP and promise P as just P for simplicity. So remember, we were always talking about promise problems. And following the famous hardness versus randomness paradigm, we know that hardness of functions implies derandomization of BPP. And this is a consequence of a very beautiful, elegant line of research, including Bloom-Micheli, Yao, Nissen, and so on, and very recently in Pagliazzo and Winderson. So for example, in Pagliazzo-Winderson, they showed that if the complexity class E does not have a sub-exponential size circuit for infinity many n, then BPP equals P. Well, this assumption is a very cute and elegant assumption. And in fact, it's commonly believed that this assumption is true. So we should also believe that BPP equals P. However, the question is, are we done yet? Unfortunately, we know that we are kind of far away from proving such a strong circuit lower bounds. So, and the assumptions we know that to deduce derandomization are not known to be necessary. Of course, we have some partial converses, starting with Pagliazzo-Cabanis and Winderson in 2002. So in which they showed that the derandomization implies circuit lower bounds for non-deterministic classes. However, it's not a sufficient condition. So today, our main theorem will give an assumption that is both sufficient and necessary for derandomization. And we show that BPP equals P if and only if the so-called gap conditional Levin-Kolmogorov complexity is hard. So note that we will focus on a gap problem, and we will introduce what the gap is, and we rely on the so-called conditional Levin-Kolmogorov complexity. And as we will see later on, this is really a very classic notion and has been studied in the 60s. And this is a very variation notion closely related to randomness. And note that I also put like a star behind the word hard. So we will introduce the hardness notion that we rely on. So let us introduce the notion of Kolmogorov complexity. So imagine that someone claims that, well, he rolls a giant dice, which consists of like 10 to the power of 18 numbers. And here are two outcomes of his rolling. So the first number is 123, 123, and so on. And the second number is 173 and something blah, blah. And this guy claims that, well, these two strings are random because, well, there are two outcomes of my giant dice. Well, we all know that something isn't right, right? This 1, 2, 3 strings can't be really random. But what this guy claims, well, seems pretty true. So in 65, Kolmogorov suggests that, well, let us forget about the sampling process, forget about the giant dice. Let's focus on how easy a string can be described. So for any string x, we let kt of x denote the length of the shortest program that outputs x. So as an example, we have like a beautiful picture here, seems pretty complicated, but this picture can be generated by a very short program, and this picture is actually not very random. The notion of K-complexity has a lot of amazing applications, such as proving Gödel's incomplete theorem, but unfortunately, it's uncomputable. So Levin was bothered by this, and he kind of introduced a notion in which he twisted the definition a little bit, and he obtained what we call Levin-Kolmogorov complexity. So for any string x, let kt of x denote the cost, again, the cost of the cheapest program that outputs the string x. But here we kind of have a new definition for the cost of the program. So the cost is defined to be first the length of the program, which is roughly the same as Kolmogorov complexity. In addition, we add the logarithm of the running time of the program into the complexity measure. So the intuition behind this definition is that first we charge for the size and the running time simultaneously. And by doing this, we make sure that this new complexity measure is computable. But we only charge logarithmically for time to capture the intuition that polynomial time computations are cheap, and it should only add a of log n term into the complexity measure. So more formally, we need to fix a new universal Turing machine U to make sure that this notion makes sense. Just think of like Python or any of your favorite programming language. And kt of x is defined to be the minimal of length of pi plus logarithm of t, satisfying that the program pi, when simulated on the universal Turing machine U, will output the string x within t steps. And in addition, we actually need a conditional variant of kt. So now let's imagine that we have some auxiliary information, which is a string z, that is kind of in the sky, and it's kind of free to get access to this string. So in some sense, we ask, what's the price for the string x, even if we give you the string z for free? So now the kt complexity of x conditioned on z is defined to be, again, the cost of the cheapest program, but this program will output x on input the auxiliary information z. So basically, well, I have z for free, so what's the kt complexity of x? So this is a notion we rely on. And let us introduce the gap problem. So the gap problem, gap MCKTP, is parameterized by two parameters, which are t yes and t no. So t yes is the threshold for yes instance, and t no is again the threshold for no instance. So the yes instances of the problem will include pairs of x comma z of the same length, and kt complexity of x conditioned on z is at most t yes. And we define no instances in roughly the same way. So now let us introduce the hardness notion that we rely on. So we will be needing like a so-called almost all auxiliary inputs hardness of gap MCKTP. So why we call it almost all auxiliary inputs hardness? So we say that for any probabilistic t-time machine M, so t is again a parameter describing how hard this problem is. And for all sufficiently large auxiliary input z, there exists some string x of the same length, such that n fails to decide whether x condition on z has large kt complexity or has small kt complexity. And we don't care about the string of complexity in the middle. So again, we call it like almost all inputs, almost all auxiliary input hard, because we put like a for all quantifier in front of the auxiliary input string z. Or alternatively, we can think of it as being worst case hard, but with respect to every auxiliary input z. So this is going to be the hardness notion that we require. Now we are ready to state our main theorem. So we basically show that hardness of a CKT complexity characterizes derandomization. We show that there exists a constancy such that BPP equals P if and only if gap MCKT with threshold of log n m-1 is almost all auxiliary inputs hard with respect to n to the c time probabilistic algorithm. So let us put some remarks here. This gives the first full characterization of derandomization of BPP. So the assumption we have here is both sufficient and necessary. And second, as we can see, we require hardness with respect to like almost all auxiliary inputs. And in the paper, we actually show that this can be relaxed. And we only require hardness with respect to a universal sequence of computable auxiliary inputs. And we'll discuss this later. And third, our characterization can be extended to also capture quasi-polynomial time derandomization of BPP, but it fails to extend to the extremely low end that we don't know how to characterize when BPP can be derandomized into sub-exponential time. And let us mention some related work here. And a very recent elegant work by Chen and Tell that shows that derandomization can be deduced from almost all input hardness. So they show that almost all input hardness of a shallow function with certain efficiency requirements implies BPP equals P. So in more detail, this shallow means that this function can be computed by log space uniform circuit with steps smaller than n squared. And they also showed a partial converse, that is almost all input hardness is also necessary, but without the Shannon-list requirements, so they fail to obtain a full characterization. And our assumption here, yeah, it is inspired by Chen and Tell and is a bit more complex. And another recent work by Hilhala showed that the equivalence of heating set generators and hardness of KT without conditional. So this very elegant result was stated with respect to low-level circuit classes, and it actually also extends to P/poly. So he showed an equivalence of HSG and hardness of KT with respect to non-uniform attackers. And we know that such heating set generators are not known to be implied by derandomization, and therefore this is not a sufficient and necessary condition. And now let us briefly sketch the proof of our main theorem. So we'll discuss how the equivalence between 1 and 2 is proved. So first, let us prove the first option. So we show that hardness of gap MCKHP will imply BPP equals P. So to derandomize BPP, we know that it suffices to prove that RP equals P. So this follows from the result of Sipser, Lortman, and Berman and Footnote. And we know the existence of a efficient heating set generator that takes a C log n bit seed and outputs a n bit string, and it fools linear side circuits. And so such a heating set generator will, if it exists, will gives us a RP equals P. However, we know that this thing is not a, well, it's perhaps it's not implied by derandomization of BPP. So as observed by Goldlack, it is actually enough to construct a weaker primitive called targeted heating set generator. So again, a targeted heating set generator is an efficiently computable function that takes a n-bit string target and a C log n bit seed, and it outputs a n bit string. So it will satisfy the so-called targeted heating property. So we require that the outputs of heating state generator will hit at least one of a y on which this m will output 1 if the machine m accepts at least a 1/2 fraction of string and machine m runs in linear time. And in addition, we'll give both h and m a target string z, and we require this heating property holds on almost all sufficiently large z, and for all machine m. So it's basically heating set generator and with an additional target. So lemma here says that a targeted heating set generator implies RP equals P. So we can just imagine derandomizing a RP with a heating set generator, but the input on which, or like the instance on which we wish to derandomize, will become the target for both the heating set generator and the distinguisher. So now we only need to construct a targeted heating set generator, and let me show you how this is constructed. So on input a target string z and a seed I, pi, s, where this z is of length n, and I is an integer smaller than O of log n, pi is a string of length I, and s is a string of log n. So we can see the target is of length n, and the seed together is of length of log n. So our heating set generator first interprets the string pi as a program, and it runs it on input z for 2 to the power of log n steps. And we let y denote the outcome. And we let ECC be a good error correcting code, and we compute g to be the error corrected of y, and we view g as a truth table of a hard function. And then we simply output the outputs of Nielsen-Windowson PRG on input the seed s and instantiate it with the hard function g. So this is going to be our construction of heating set generator. So now let's prove that it works. So we assume for contradiction that there exists a distinguisher d and infinitely many target string z on which d breaks heating set generator h. Note that by breaking heating set generator, we mean that this distinguisher d will output 0 on any output of heating set generator, but still accepts a 1/2 fraction of strings. And now we're going to show that on input x, z, using the distinguisher d, we're going to decide whether kt of x conditional on z is very small or is very large. So let's look at our reduction. So to decide this gap problem on input a pair of x, z, we need to decide if, well, the complexity is large or small. First, we compute f as error corrected or a error corrected version of x. Then we run the Nielsen-Windowson reconstruction algorithm for NW PRG with instantiated with the hard function f and with the help of the distinguisher d. And this d, we know that the target string of d is d. And we also run the decoding algorithm for the ECC. So while this Nielsen-Windowson reconstruction algorithm will give us a string, will give us a string, and we output 1 if what we obtain from the reconstruction algorithm is the string x, and we output no if we don't get the string x. So this is basically the reduction. And now let's analyze this reduction for a bit. So if x, z is a yes instance, and we know by the construction of our heating set generator, the outputs of NWPRG with f will be in the range of heating state generator. And this means that the distinguisher D will also distinguish the NW PRG from random. And by reconstruction algorithm, we know that we will reconstruct the string X, and therefore we are going to output 1. So if what we get is a null instance, and by the property of Nielsen-Williamson reconstruction, we know that any string recovered by the step 2 will have like a succinct representation or like a short description, which means that any string obtained by step 2 will have Kt-Complexity, well, very small, say square root n, conditioned on Z. And therefore, since X, well, is a null instance, and we will never recover such X, and we will output null. So this basically concludes the proof for the first direction, and we know hardness of MCKTP implies BPP equals P. And now let's briefly look at the proof for the converse direction. So for the proof consists of 2 steps. Step 1, we know that by Goldlack, he showed that if BPP equals P, then there's a targeted PRG. So a targeted PRG is just a normal PRG, but it has to be secure on every target string. And in step 2, we show that a target PRG will imply this gap MCKTP problem is almost all auxiliary inputs hard with respect to n to the c time probabilistic algorithm. And note that this almost all auxiliary input hardness comes from the fact that this PRG, the targeted PRG, will be secure on every target string. So our main theorem says that there's a constant C such that BPP equals P if and only if gap MCKTP with thresholds of log n and m-1 is hard on almost all auxiliary inputs with respect to n to the c time probabilistic algorithms. And to conclude, the hardness of conditional Kt-Complexity characterizes derandomization, and this is the first hardness assumption that gives a full characterization. And we want to discuss our main theorem a little bit. So first, on the hardness assumption that we rely on, note that we require hardness on almost all auxiliary inputs. So in some sense, we require hardness of a family of problems. We can imagine that there's one single problem for each auxiliary input sequence. So the hardness on all auxiliary input sequence is basically says that we require hardness of a family of problems, and every problem in this family should be hard. So this is not a single problem. So in the paper, we show how to relax this. That's in the sense that first, we only need to consider computable auxiliary strings as opposed to all auxiliary strings. And hardness with respect to a single sequence is good enough for us, but unfortunately, it's not a natural one. So we left it open to show that to find a single problem which characterizes whose hardness characterizes derandomization. And on low end setting, our characterization does not extend to the low end regime. So we don't give a characterization of when BPP can be derandomized in sub-exponential time. So in upcoming results, we basically find such a assumption. So we call it leakage resilient hardness. And we show that BPP equals P if and only if there's a polytime computable function that is almost all input leakage resilient hard. So due to the limit of time, I won't be able to tell you what leakage resilient hardness is, but let me put some remarks here. So, well, this gives a characterization with respect to an existential assumption. So any hardness of any such function suffices. So we don't need hardness of every problem in a family. And second, this characterization extends also to the low-end regime, to derandomization of MA, to average case derandomization. And finally, this result in some sense explains by how much the IW assumption, namely E is not contained in sub-exponential side circuits, might overshoot the problem of derandomizing BPP. And thank you for your listening.